Consider a multivariable function f in variables x1, x2, x3, so on till xn. And this is to be maximized or minimized under these constraints. So you have equalities as restrictions on our variables. That is, they limit the kind of values that your variables can take. So the first constraint is that g1, which is a function. So g1 of x1, x2, x3 all the way to xn, that is 0. So for example, x1 plus x2 equal to 0, that would be a restriction. And then you will just say that g1 is equal to x1 plus x2 because we are setting that to be equal to 0. Another example would be when you have x1 squared plus x2 squared equal to 1. Then you would just set g1 to be x1 squared plus x2 squared minus 1. So you have these restrictions. Here gi for all I belonging to 1, 2, 3, so on. This is also a multivariable function, as I said. Thus, the question is the same as finding minima or maxima in these variables x1, x2 till xn of a function capital F, which is given by small f plus alpha 1 g1 plus alpha 2 g2 and so on, where alpha 1, alpha 2, so on. These are constants with respect to the free variables. So our free variables are of course x1, x2, x3, so on till xn. So these alpha values, these are not changing with respect to these variables, and thus these are constants. Yeah, and we have to maximize or minimize this function capital F under the same constraints. That is g1 equal to 0, g2 equal to 0, so on. So that, yeah, that's the same thing as maximizing or minimize small f, because capital F is equal to small f, right? Assuming that these constraints are actually applicable. All right. Now consider another function, capital H. So this is once again a function, but now it has more variables. This is a function of x1, x2, x3 till xn, and then lambda 1, lambda 2, so on. And let's just say that this function is equal to small f plus lambda 1 g1 plus lambda 2 g2, so on. Here we're considering g1 as a multivariable function. Lambda 1 is a free variable, and yeah, the same stuff for every other term. Small f is just what we defined, right? So under no restrictions in these free variables that this h is a function of, our capital H attains maxima or minima whenever the partial derivatives of h with respect to all these free variables, those are equal to 0, right? Now that's the same thing as these equations. The first thing you get by differentiating this with respect to lambda I is that gi should be equal to 0. And secondly, when you differentiate with respect to xi, you will get some kind of equation in these free variables, and you will get such equations for each xi value, for each xi free variable, right? Suppose the solution to this system of equations is this thing x1, x2, x3 till xn. These free variables have the values a1, a2 till an. So this is the solution, right? A solution, I should say. And you have lambda 1, lambda 2, so on. That's equal to b1, b2, so on, right? So here you might have just one solution, right? And it might, so you have more solutions. We don't know yet, right? We don't know yet. But then you can see that the number of equations that you're going to get, those are equal to the number of variables. So it's okay to assume you will get just a single solution, right? Okay. Then you have these things. So for lambda 1, lambda 2, so on, right? These fixed as b1, b2, so on. There is no x1, x2, x3, so on till xn in the locality of a1, a2, a3 till an, such that it gives a bigger or smaller value of h than this a1, a2, a3, right? This set. Yeah. So if you are finding the maxima, then of course no x1, x2, x3, xn, right, so on. In the surrounding of this thing, right, no such ordered pair is actually going to give you a bigger value than what we get on this thing, right? That's why it would be a maxima. And similar thing for minima. Just now it's like not giving you a smaller value, right? Yes, because when you set lambda 1, lambda 2, lambda 3 equal to b1, b2, b3, so on, and then you look at this h function, right? Then this just becomes a function in the free variables x1, x2, x3 till xn, and not these variables x1, x2, x3 till xn, and lambda 1, lambda 2, lambda 3 till lambda n. So that's yeah, that's actually altering this definition because now it's making a function of less variables, right? By setting lambda 1, lambda 2, so on to be constants. And yeah, because it's following these restrictions and it's following these it's having this property that no other ordered pair of xi give bigger or smaller value depending on what you're trying to find than our um, ordered set of AI, right? So yeah, this thing a1, a2, a3 till an, that ordered pair or ordered set or whatever. So that means that actually this a1, a2 till an, this thing, this ordered pair is actually the minima, right? So when you will yeah, so this capital H under this restriction that lambda 1, lambda 3, right, these things are constants. It has our minima or maxima being this thing a1, a2 till an, right? But now if you think about it, what we just did is we figured out um, the minimum or maximum of our small f as well, because right, yeah, because it's following these restrictions. Our g1, g2, so on, these values are just zero, so our capital H is actually equal to our equal to small f, right? Yeah. So now if we set alpha I to be equal to bi for all I belonging to 1, 2, 3, so on, then 1 basically says, so 1 was this thing, where did that go? Right. So 1 is that for all lambda I fixed as bi, there is no xi ordered set in the locality of ai ordered set such that you get a bigger or smaller value of h, right? So basically 1 is just saying that this thing is a maxima or minima of capital F, right? Of course, that is assuming that you define it using alpha I equal to bi, right? So yeah, we didn't actually tell you what alpha I, alpha 2, right? What these things are. We just said these are constants with respect to your free variables. We didn't say what the values of these things are. So what if we set these to be equal to bi, right? Then that definition of capital F, right? That just has its minima or maxima um, at this at this set of values, that x1 equal to a1, x2 equal to a2, and so on, right? But then we already said that whenever capital F attains a maximum or minima, small f also attains a maximum or minima. So our small f will attain maximum or minima when these conditions are met. When you have alpha I equal to bi, and when you have xi equal to ai. So to figure out ai, you can make a function capital H like this, and then write down these equations, solve that set of equations, and then whatever values you will get for our ai, right, that is the maxima or minima for our small f and capital F. All right. So capital F as, yeah, that just attains the maximum or minima. Right. All of this basically says the same thing. Now here's an example of this. So let's find the maximum value of 4x plus 3y under the restriction that x squared plus y squared equal to 1. So this can be done using trigonometry, right? Writing everything using a single variable, right? Or you can do geometry if you understand what's actually going on. It's like a dot product over here, 4 comma 3, that vector dotted with x comma y, and over here you just have a circle. So you are talking about a point or a vector on a circle, and then taking a dot with some certain vector in some certain direction, right? So it's common logic that this will be maximum whenever your x comma y, that vector points in the 4 comma 3 direction, right? So yeah, I mean, you can already say that x comma y, that vector, that must be 4 upon 5 comma 3 upon 5, something like that, or negative 4 upon 5 and 3 upon and negative 3 upon 5, but that will just give a negative value, which is not what we want. We want a maximum. So that's why 4 upon 5 comma 3 upon 5. But we can also do it using the Lagrange multiplier method. So here we'll just say that our small f, which is the function that you want to maximize or minimize, that is 4x plus 3y, you have only a single restriction, which is that g of x and y equal to x squared plus y squared minus 1, that has to be equal to 0. That's our restriction. So now we'll just make this capital H function, which will be our small f plus this lambda thing times g. And by the way, these lambda things, these are actually called Lagrange multipliers, and that's why this is called Lagrange multiplier method. Okay, cool. Right. So we'll basically make this capital H function. Then we do the whole process that will take the partial derivative of capital H with respect to x, and then y, and then well z. So I don't think that's supposed to be z over there. Where is that z? Oh, it should have been lambda, I think. Right. So yeah, this should have been lambda and not z, but whatever. Anyway, so when you take these partial derivatives with respect to x, y, and this other free variable lambda, you will get these equations, right? And then solving these equations, we'll just get xy is equal to minus plus 4 upon 5 minus plus 3 upon 5. So these minus pluses are actually linked. That is, if this thing is minus, this thing is also minus, and this thing is plus, and this thing is also plus. So of course, the maximum value is when you have plus, because that will be positive, and with the minus values, you just have negative, which is actually the minimum value. That's not what we want. So the maximum value is just 4 times of 4 upon 5 plus 3 times of 3 upon 5, right? And thus you get 5 as the maximum value. Consider n particles, with each particle having x component velocity vi for I belonging to negative infinity to infinity. I is just a marker to tell us which particle we are dealing with or which velocity we are dealing with. This range has nothing to do with the derivation. You can use any range that you want. You could even have I like equal to 1, 2, 3, 4, right? So yeah, just because there are infinite number of such cases, right? Infinite such velocities. That's why I'm dealing with this range, all real numbers. Anyway, so let the number of particles with vi be small ni. So vi is a certain velocity, and then for that velocity you have small ni particles. We are till now dealing with a discrete distribution, so we don't have a range for our velocity. Instead, we have discrete velocities, just infinite number of them, right? So number of particles with vi, that is ni, and then summation of small ni, that's equal to capital N, that's the total number of particles. Okay, if the whole system has x component of velocity v center of mass, and rms of vi is vrms, then capital N times vrms squared is equal to summation of ni vi squared. So by definition of what vrms actually is, and then n v center of mass is equal to summation from I equal to negative infinity to infinity of ni vi. So the total momentum, right? Just calculate that and then divide by the total mass, right? And then you get this thing. So each particle is of same mass. We are assuming that this whole derivation is completely for ideal gases, right? Okay. Where of course capital N is equal to summation of ni, right? I just said that. Anyway, so the number of microstates, that's given by capital W equal to capital N factorial upon the product of these ni factorial. This is the number of ways to choose sets of ni particles for every vi. Also, you can apply natural log on this thing to get natural log of W equal to natural log of N factorial minus the summation of natural log of Ni factorial. Our assumptions are these. Every small ni is actually much bigger than 1, but it's also much less than capital N, because as I told you, there are infinite number of vi, right? So then applying Stirling's approximation, which is something you should be knowing. So the Stirling approximation basically says that natural log of n factorial, that's equal to n natural log of n minus n, where n is a very big number, right? So in this case, natural log of w, that is equal to this thing. We can write that as approximately n natural log of n minus n minus this summation. It contains these things, summation of ni natural log of ni minus ni. Then you can break this summation and then remember that summation of small ni is just equal to capital N. And then you can clean up some stuff to basically get this thing. Capital N natural log of capital N minus summation of ni natural log of ni. So according to second law of thermodynamics, we must have maximum value for this capital W for equilibrium, that is. So to maximize this small f is said to be equal to capital N natural log of n minus summation of ni natural log of ni. So of course, capital F, small f is just natural log of w, but in a approximated form, right? So we have some restrictions. First of all, we have the restriction that capital N should be equal to summation of ni, right, from the definition. Then you also have these two equations as restrictions themselves. So all these three equations, these are actually restrictions. So under these restrictions, you want to maximize the value for our small f, which is just natural log of w, right? So to do that, we'll use the Lagrange multiplier method. So we'll set capital F to be equal to small f plus alpha g1 plus beta g2 plus gamma g3, where alpha, beta, gamma are our multipliers. Then we'll take the partial derivatives with respect to our free variables. So first variable will be ni, right? Every ni basically. So n1, n2, n3, n negative 1, whatever, right? Just take our partial derivatives, set it equal to 0. So what that will give us is natural log of ni is equal to negative alpha, negative 1, minus beta vi minus gamma vi squared. So we can write small ni equal to e power negative alpha, negative 1, negative beta vi, negative gamma vi squared, right? And then using this equation for our restrictions themselves, so you can just put ni equal to that value into this equation, or all these equations in fact. So what you will get is small ni upon capital N, that's equal to vrms squared, this exponential which is dependent on our ni, and then upon the summation of vi squared e power negative alpha minus 1, right? All that stuff, the same exponential once again, right? And this is from this equation, of course, the RMS velocity, right? The equation for that. So first equation. Okay. Now let's define xi to the fraction of particles with velocity less than vi. So of course we are only dealing with the x component only. We are not talking about 3 dimensions for now. We'll talk about that, but later. All right. So if we define xi to be the fraction of particles with velocity less than vi, then ni upon n, so small ni upon n, that's equal to delta xi, right? So you could always say that, let's just say small n is, or I don't know, small ni dash, that's the number of particles which have velocity less than less than vi, so not the fraction but the actual number. Then small ni is equal to delta ni dash, right? And then that divided by capital N, so that's like, yeah, delta of ni dash upon capital N, and that is delta xi, right? So this is no big brainer, of course, right? And now using this thing, you can actually write delta xi upon delta v. So this delta v I actually divided by that, right? Originally this equation was just delta xi equal to all of this, but then I divided by delta v forcefully because we'll be needing that later on. Okay, so you just have delta xi upon delta v equal to this, right? So you have vrms squared times this exponential. So this is dependent on the I value. So which vi are you talking about, right? Yeah, and this summation, so this is the summation of vi squared e power this exponential, right? So this part is dependent on the v itself, and then you have delta v. But then if you think about it, the summation is over infinite number of such v values, right? So this very much looks like an integral, doesn't it? So moving to a continuous distribution, you can actually change this summation for an integral. Just have the integration from negative infinity to infinity. So as I told you, I chose negative infinity to infinity with the range for I, because I also wanted some representation for the cases when your particle is moving in the opposite direction to what is positive, right? That's why negative infinity to infinity of v squared e power, okay, all that exponential once again. Now I'm just replacing vi with v because we all know what v means in the continuous distribution and what is it in this context, right? So dx upon dv, that's the fraction of particles in the range v to v plus dv, right, which have velocity in that particular range, upon dv, right? So that's our f of v. So this is our probability distribution function, All right, and in a continuous distribution, this thing on the right hand side turns out to be this. So you got vrms squared e power negative alpha minus 1 minus beta v minus gamma v squared, and then this integral. Yeah, this summation turns out to be an integral, right? It's no big deal. It's done a lot in maths. Okay, so now we can get rid of this e power negative alpha minus 1 because that's a constant. You can take that out of this integral and then you just get this thing. Vrms squared e power negative beta v minus gamma v squared upon this integral. So once again, a reminder, v is the velocity of the range you are talking about. So the range is of course v 2v plus dv. So in that, how many particles you have, or what's the fraction of particles you have in that range upon dv. That's what we're talking about. That's our f of v, right? So yeah, the v from that range, or the average velocity in that range, right? That's what we are saying to be our v in this right hand side as well. Okay, cool. Then first of all, we just need to figure out what this integral is going to be. So what is this integral? Integration from negative infinity to infinity of v square e power negative beta v negative gamma v square. You can break this as v e power negative beta v and then v e power negative gamma v squared. So this part can be integrated because you have a v over here. You just need 2v dv. So you can get like v squared, right? And then this part, we don't know what to do with it. We'll just differentiate it. Okay. So doing the integration of parts, you basically get this thing. You just get 1 upon 2 gamma integration from negative infinity to infinity of e power negative beta v negative gamma v squared dv. Let's call this thing I2. So first of all, we need to figure out what I2 is. So I2 is a Gaussian integral. And in case you don't know about this, just search it on Wikipedia or any place where you get information on this thing. It's actually not that hard to understand. You actually need to think of the integral in two variables. So multiply the integral, right? First write it using x and then using y, and then you have to write it in polar coordinates, and then you'll get this value. So it's not that hard. Just search for it. A lot of people have videos for it, right? And yeah, I'm just gonna tell you what this integral actually has its value equal to. So integration from negative infinity to infinity of e power negative ax squared plus bx dx, right? This thing is just square root of pi upon a times e power b squared upon 4a. Now applying this equation for this integral, you just get I2 equal to square root of pi upon gamma e power beta square upon 4 gamma. So thus I1 can be written like this thing. Okay, and then using that you can write our f of v, which was just this thing, right? So just this vrms squared e power negative beta v negative gamma v squared upon I1. That thing just becomes this 2 square root of gamma cube upon pi vrms squared e power negative gamma v squared negative beta v negative b squared upon 4 gamma. This thing is a constant, right? Okay. Also, we know that the integration from negative infinity to infinity of f of v dv equal to 1, right? Because the way we define f of v is dx upon dv. So f of v dv is just dx, and when you integrate dx for all kinds of ranges of v, you are just basically adding up all these mole fractions, and then in the end you just get 1, of course. All right. Okay. So then you can write vrms squared upon I1 times integration from negative infinity to infinity of e power negative beta v negative gamma v squared dv to equal to 1 from this integral, from this equation, of course, because our f of v is just this thing, right? Yes, I think that's how it should be. Okay, so then you just get this thing, vrms squared times I2 upon I1 is equal to vrms squared times 2 gamma, right? And that's equal to 1. So you have this I1 over here. I'm not writing the whole value of I1, but yeah, if you want, you can write the whole value. It's just a lot of work, so why even do that when you are going to get I2 upon I1 in the end, and you will have some cancellation to get, right? Why even write the whole value? Okay, so of course this integral that was I2 from the very start, it was just I2. Basically, you just get this thing that vrms squared times I2 upon I1, that's equal to 1, and we know that I2 upon I1 is just 2 gamma. So basically what you get is like VRMS squared times 2 gamma equal to 1. So this equation actually tells us what gamma should be. So till now we don't know what alpha, beta, gamma should be, but now we know. So now we know something about it at least. We don't actually care about alpha at all because that's cancelled from the very start. Right, so we only care about beta and gamma. Now we know what gamma is. We also need to know what beta is. We'll figure that out soon. Okay. So now that we know what gamma is, we can put that again in our f of v, right? And now with the new definition, so we can go for some other constraint. So the other constraint we're talking about is that second equation. So the capital N V center of mass equal to the summation of Ni Vr. We can use that. And by the way, usually the center of mass velocity, we just let that be equal to 0, right? Because we are talking about stationary boxes of gas. But let's just go and see what happens when you actually don't have the center of mass equal to 0, right? What happens to the distribution and all that stuff. Okay. All right. So this equation can be written in this form in the integral, right? So where v center of mass is just integration from negative infinity to infinity of v f of v dv, right? Once again, the same thing as what you have for the center of mass equation, right? Yes, like the total mass, that's now like total number of particles. Well, that times of the center of mass's velocity, that's equal to the summation of Ni Vi. That's what we said. But now you can actually write Ni as right. So Ni is of course is dx, and that's just equal to f of v times dv. So this thing is our Ni part, and then you have Vi, which is just now just v. So that thing, and this summation turns out to be an integral now in our continuous distribution. So v center of mass is just this integral. We can calculate that, right? So just get this. Yeah, just a lot of math basically. So using that, you can actually get what beta is, because now we know what gamma is. So yeah, just get beta equal to negative v center of mass upon VRMS squared. Okay. Now, once again, doing a bit of maths. Yeah, like, dealing with some stuff. Okay. So you have this thing, 2 square root of gamma cube upon pi times VRMS squared. That's equal to 1 upon square root of 2 pi VRMS. And then you also have v squared upon 4 gamma is equal to v center of mass squared upon 2. So why are we doing all of this? Because we want to get that f of v thing. So where did that go? Right. So f of v is basically this thing, right? Yeah, and we actually want to get what this thing is. We already got what this integral should be, right? So we got what I1 is. Where did that go? Right, so like I1 equal to this. Yes. So where's our final equation? Okay, this thing is what we're talking about. So f of v is equal to 2 square root of gamma cube upon pi and then VRMS squared and all of this stuff. So we don't want gamma and beta. We instead want v center of mass and VRMS to be the parameters we'll be dealing with, because we don't know what gamma and beta are, right? Okay, now we actually figured out what these should be. So we just plug those values in this. And that's why we are figuring out what square root of gamma cube upon pi should be and what these values are, right? Okay. So basically you just get this stuff. This 2 square root of gamma cube upon pi times VRMS squared, that happens to be 1 upon square root of 2 pi times VRMS when you put the value of gamma in this. Then beta squared upon 4 gamma, just put the value of beta and gamma. You just get v center of mass squared upon 2 VRMS squared. Then beta times v, that's equal to this thing. Gamma times v squared equal to that. Alright. So finally the exponential part, or the negative of the part on the exponent, right? That's equal to this thing, v minus v center of mass squared upon 2 VRMS squared. So you can finally write that f of v is equal to, of course, this part times e power negative of all of this stuff. So this just becomes this thing, 1 upon square root of 2 pi times VRMS. Well, that times e power negative. So negative, by the way, right? Negative of this thing. So finally our f of v is just this. Once again, f of v is just dx upon dv, right? And that's equal to this thing. Cool. Now, just to make some simplifications, we just set v center of mass to be equal to 0. So now that we know what's actually going to happen when center of mass is not 0, we can actually set it to be equal to 0 so that we can go into more equations, right? So let's just set v center of mass to be equal to 0. Then this just becomes f of v is equal to e power negative v squared upon 2 vrms squared upon square root of 2 pi times vrms. But from equipartition theorem, we know that the kinetic energy is just half m vrms squared for, of course, the x direction, and for a certain particle on average, it's just this thing. Okay, I know there's a lot of conditions, but let's break it down. First, you must have this for a single particle. That's why I'm using small m and not the total mass of the thing. All right. Then this is the average kinetic energy. That's why I'm using vrms squared and not v squared. And this is for only the x component. That's why I'm using the vrms squared for x component only. So by the way, the energy for x, y, and z components, well, these are actually independent. So you can write total kinetic energy as the kinetic energy from the x component plus the kinetic energy from the y component from the z component. Cool. From equipartition theorem, we know that this k thing is equal to half kt. So this k and this k are very different. This k is the Boltzmann constant. This is the kinetic energy. So that's why it's a capital K. So this is equal to half kt, right? Thus you just have vrms squared from this equation, of course, is equal to square root of kt upon m. Now putting that into this equation along with v center of mass equal to 0, what you get is f of v sub x. So I'm using v sub x now because we'll be dealing with the complete distribution very soon. So the actual speed distribution and energy distribution, and not just distribution in the x direction or only the y direction or only the z direction. Right, so you just have f of vx, or if you want, you can write f sub x of v sub x, so that it's only the distribution in the x direction, right, to signify that. Anyway, that is just equal to square root of m upon 2 pi kt times e power negative m vx squared upon 2 kt, right? Just putting everything into this thing. Okay, now we can use this to figure out how our natural log of w, which was our small f, of course, how does this change with our RMS? Because we just know how this is actually behave. It's going to behave with the RMS velocity, right? Yeah. Okay. So in the discrete distribution, we had natural log of w is equal to n natural log of n minus the summation of ni natural log of ni, right? The approximated value, of course. This should be an approximation, but like whatever. Okay. Then taking the partial derivative with respect to the RMS. So this is for discrete distribution, by the way. Okay. Taking the partial derivative, just get this thing. Just get negative summation of natural log of ni plus 1 times dni upon d vrms, which is just negative summation of natural log of vrms times sort of 2 pi times ni upon capital N times delta v times dni upon d vrms. So first of all, why is this square root of 2 pi over there? What exactly happened? Well, I just used the thing that we got from this thing, from the continuous distribution. I just extended that to our discrete distribution as well, right? So then you can write ni as equal to capital N times f sub v, or f of v sub I, right? So f of v sub I, we know what value that should be, right? You could say it's more like an approximation and less like an actual thing, but whatever. So yeah, right. So you can use that. You can use that and actually get rid of some stuff. So this is just natural log of vrms times square root of 2 pi times ni upon capital N times delta v summation. Sorry, and then you got this thing dni upon d vrms. So basically this thing, natural log of ni plus 1, I just changed this, right? Yeah, of course. And of course, like this 1, so when you do this thing, the summation of 1 times dni upon d vrms, well, the summation of dni, that is equal to capital N, and that's not actually changing, right? It's not changing. So I haven't wrote that down in this bracket. So because this summation of dni upon d vrms equal to d capital N upon d vrms, which is not, I mean, like, yeah, capital N is not changing. So you can write actually, this is just equal to 0, of course, because the rate of a constant is just 0. So this one part, we don't really care about it. We just care about what natural log of ni should be. So then you replace some stuff. Okay, so this is, oh, and by the way, this thing, vrms times square root of 2 pi, and then this capital N times delta v, well, this is all constant as well. So you actually don't have to worry about that really. Yeah. So you can pull that outside as well, and then by the same logic, we can get rid of all that stuff, right? And now we can input what ni should be. Okay, actually not yet. We'll still have to do some stuff, right? So you got this as our equation now. So you can convert that to an integral, right? So first we'll just write it in the form that's best to convert it to an integral. We'll write as negative capital N summation natural log of VRMS, that times of sort of 2 pi, that times of Ni upon capital N delta V. So Ni upon capital N is just equal to our dx in the continuous distribution, and delta V would be our dv, right? So that's our f. So you could directly input what Ni is using our f times capital N, the f times delta V stuff, right? So you can use that as an approximation, or you could use this thing. You can just convert it to an integral first and then use the thing that you got for the continuous distribution. Anyway, so we'll be going for the second part, it seems. Okay. So you got natural log of w upon, okay, the derivative of natural log of w with respect to VRMS, that's equal to this thing, negative capital N summation of natural log of VRMS square root of 2 pi Ni upon capital N delta V. So all of this stuff, right? That times d upon d VRMS of Ni, right? But then you can replace Ni by this thing. You can write it as like d Ni. Okay, this is not what I want. Right, we can write it as d Ni upon delta V. Well, that times of delta V once again. So this should not actually be, okay, fine. DNI is not that bad. So this is with respect to VRMS, right? So it's actually a differential. Even though we are not in continuous distribution yet, it's actually a differential because this is with respect to VRMS. Okay. Then you got this upon capital N delta V, and that's of delta V, of course. So yeah, well, Ni upon capital N times delta V, right? That would be our f of V, and then the derivative of that with respect to V center of the VRMS. That's usually what this thing is, because our delta V is independent of how we change the VRMS really, right? So this thing really is just the derivative of f of V with respect to VRMS. Okay, then you got delta V, which will change to dV, and then of course we divide by capital N over there. You have to multiply by capital N as well to keep the equality, right? And then you can write it as an integral. You just get negative capital N integration from negative infinity to infinity natural log of this stuff. So just VRMS square root of 2 pi times this thing is just f of V, and that times of this. So this little part, the d upon d VRMS of this bracket, that's the same thing as the partial derivative with respect to VRMS of our f of V. All right, and then delta V is just dV. So this dV is for this integral, and then this is yeah. So whatever value you will get after doing this partial differentiation, you have to input that, and then you have to calculate this integral. Right, that's what it actually says. Right. So then doing the math completely, you just get this thing. It's equal to capital N upon 2 square root of 2 pi VRMS power 6 integration negative infinity to infinity of V power 4 minus V squared VRMS squared e power negative V squared upon 2 VRMS squared dV. It looks intimidating, but just try it out. Try out this complete integrand, right? Try to see what it simplifies to. Put in the value of f of V. Put in the value of f of V over here. Take the partial derivative, right? Simplify it. You'll basically get this integrand. All right, cool. Okay. Now let V be equal to x VRMS, right? So this x is actually different than the fraction. So it's different than the mole fraction really. Okay. So then if you just set it to equal to this thing, some number x times VRMS, this is happening for each V value, right, in our range. Yeah. Then you can write this whole thing as capital N upon 2 square root of 2 pi times VRMS, and then this integral. So yeah, look at this. V is equal to x times VRMS power. Yeah, like V equal to x times VRMS. So this thing is just x power 4 times VRMS power 4, then minus x squared times VRMS power 4. So you take that VRMS power 4 outside, just get VRMS squared over here. Then dV is just dx times VRMS, because of course this delta V, it was from the distribution. It was not because of the VRMS. All right. So yeah, our dv thing is just actually VRMS times dx. So no big deal with that. So what we basically get is just n upon 2 sort of 2 pi times just one single VRMS, because 4 4 was reduced because of this thing, and then one more because of that. This get capital N upon 2 sort of 2 pi VRMS, and then this integral. Now this integral is some kind of numeric value. We can actually calculate what this should be, right? So basically just moving this stuff, right, moving this stuff on that side, yeah, what you will get is this square root of 2 pi VRMS upon capital N, the partial derivative of natural log of W with respect to VRMS. That's equal to this integral, right? And that integral can be solved using division by parts, and then you just basically get square root of 2 pi as the value of this integral, right? Yeah, so basically what you get is partial natural log of W upon partial VRMS is just equal to N upon VRMS, right? So basically what it's saying is that the entropy, which is given by K natural log of W, right, that follows this equation. And once again, K is just the Boltzmann constant. So the entropy follows this equation, partial derivative with respect to the VRMS in the x direction. So I'm using the subscript x because you can get the same kind of equation for each direction for y, z, right? Even for like rotational degrees of freedom, you might get the same kind of thing. Yeah, so just got partial s upon partial VRMS in the x direction, that's equal to K times capital N upon the VRMS in the x direction. Okay. Similar equations can be formed for Vy, Vz, Wx, Wy, Wx, yeah, okay. All of these degrees of freedom. Okay. But then remember that VRMS in the x direction, that's actually known using temperature, right? So we know that half small m VRMS squared is equal to half kT. So our VRMS is the square root of kT upon m. So using that, you can write this. You can write this equation using temperature alone. So yeah, just doing all of that, you basically get like partial s upon partial t is equal to summation of K times capital N upon 2t, and this is for all the modes of freedom, of course, right? So for a single mode of freedom, so for only the x direction, you just have this thing K upon 2t times capital N. So this is capital N, that's untouched, and then all of that stuff, you know, right? So that VRM is converted to T, this is converted to T as well. This K times N is still there, so you just get this thing Kn upon 2T, right? Cool. You can of course do it, you know, using a bit of abuse of notation, and then write partial VRMS x upon VRMS x as partial of T of natural log of VRMS x, and then use the fact that VRMS x can be written as square root of Kt upon m. So the K upon m stuff is just constant. So square root of T is what matters, and then it's just like half natural log of T. So the derivative of that thing, or the differential of that thing, of course, just half dt upon T, right? And then you can get this equation very easily. But yeah, whatever, just do it the proper way. Even then you get the same thing. So what basically gives us is that partial s upon partial t is equal to K capital N f upon 2 times 1 upon t, right? Because this thing is actually dependent on temperature only, right? So this is the same for every mode. Then you can just have the number of modes times this thing, right? Which is a small f, of course. So you basically get this thing, right? And yeah, this is from where you usually get like s is equal to, you know, Kn f upon 2 natural log of t. So using the abuse of notation thing, right? Okay, so also for a certain probability. Okay, so all of this is already discussed in the final thermodynamics PDF that I uploaded. So this is just for the volume, right? How is entropy dependent on volume, right? So just read that. It's not hard at all, actually. Like what we finally get is just this thing, that our entropy can be given as number of moles. Well, actually not number of moles, like number of particles. So entropy is just number of particles times the Boltzmann constant times natural log of volume times temperature power f upon 2. And of course, this is just with abuse of notation. The proper equation would be this thing, x equal to s naught plus nk natural log of pt power f upon 2 upon v naught t naught power f upon 2. All right. Yeah, so that's it. All right, so just before moving into the next section, it's worth taking a look on how probability distribution functions behave when we're not talking about a single variable, but multiple variables and also restrictions and all those things. All right. So first of all, just a recap. If you have p sub x of t as probability that the x values of an event is less than t, right? That is, it's the number of events with x less than or equal to t, or I should say number of instances of the event upon the total number of events that happened actually, right? So number of instances of the event, right? If that's how you define p sub x of t, so this is basically just a probability that when an event happens, it happens with some certain variable x less than or equal to t, right? Then let's define f sub x of t as the partial derivative of this probability with respect to the coordinate t, right? So this thing f sub x of x is the probability distribution function in x, right? Okay, consider 3D space of events with axis x, y, z, which are parameters of an event. Okay, these x, y, z are independent of each other, and so are the probability distributions in them. Right. Then the probability of an event in the volume dx, dy, dz with x, y, z as one of the corners. That is the volumetric probability, right? That's given by just the product of these probabilities in the individual directions. So x, y, z, I'm saying directions would be like these variables. So this is the probability in the x variable, this is in the y variable, this is in the z variable. So if this is close to x, y, z, right, we're talking about something that's happening in the proximity of x, y, z, or possibility of that thing actually happening, that is basically this thing, right? That's the volumetric probability distribution that's given by f sub v of x, y, z. That should be just this thing, f sub x of x, f sub y, and then f sub z. So basically just divide this thing by dx, dy, dz. So this has the property that this f sub v times tv, that's the probability that something will happen in proximity to x, y, z in a blob of volume dv, right? Okay. And the probability of events in a volume gamma, right? So gamma is some certain volume. The probability of the event happening in that volume gamma, that's given by the sum of these probabilities, which is just f sub v of dv, right? And in this case, it's just an integral, right? Also, we can actually go to the spherical coordinates. So since this dv thing, it could be any kind of volume, not necessarily cubical, might as well use the spherical coordinates to write it, right? So going to spherical coordinates, replacing x, y, z by our r, theta, and phi things, right? You can actually change your f sub v into a function of r, theta, and phi. And then you can rewrite this p sub gamma using the spherical coordinates completely, right? Once again, just dv thing, that's actually given by r squared sine phi d theta d phi dr, right? Yeah, so we basically just get this thing. This is in the spherical coordinates, of course. Okay. So if somehow your g, which is of r, theta, and phi, that's like separable, so you can write as a product of these three things. So like g sub r of r, g sub theta of theta, g sub phi of phi. So g sub I, right? So for example, g sub r, that is only dependent on I. So g sub r is only dependent on the r thing. It's not dependent on theta at all. So for example, r squared would be something that's dependent on r and not theta, while r squared, or let's just say r plus sine theta squared, that would be dependent on theta. So you don't have those things. Then you can actually separate this integral into three integrals and multiply those together, because this, yeah, right. So you can just write it like this thing, the integral of g sub r of r, and then you got r power 2 dr, well, that times of this integral, g sub theta of theta times d theta, then you got g sub phi of phi times sine phi d phi. Once again, this kind of separation that requires some stuff, but that will be met if your gamma is a sphere of radius capital R, right? So if it's actually a sphere of radius R, then you can definitely just separate it. You'll get P sub gamma is equal to this product of these three integrals. The first is just this integral in a radius completely. It's going from 0 to some capital R. So the capital R was the radius of this complete sphere. Then you got this integral in theta is going from 0 to 2 pi. As you can see, it can go from 0 to 2 pi. So we'll consider the whole volume of the sphere. That's why the minimum to maximum value. And similarly for phi, it's going from minimum to maximum value, just 0 to pi, right? Okay. Right. So now if g sub theta and g sub phi are constants, that is to say that this g of r theta and phi, this is actually only depend on your radius. It's not depend on theta and phi at all, right? If that somehow happens, then this g sub theta, g sub phi, you can actually set these to be 1, right? Because when you when you separate these things, you have some freedom in deciding like whether or not you want to take some constant from here. So for example, this is like 2 theta, this thing is 2r, right? You can take that 2 from this thing and then put that in there. So you just get like 4r times theta. So 4r is this first part, then theta is this second part. Instead of having 2r is this first part and 2 theta is the second part, right? You can do stuff like that. So, if these are actually constants, pull out those constants from these constants and make them 1, right? So this thing is just gonna become like 0 to 2 pi of 1 d theta, which happens to be 2 pi. And similarly, this thing will just turn out to be sine phi, d phi, the division of that guy from 0 to pi, right? Which is just 2. So basically, you just get like d sub gamma is equal to 4 pi times this integral, right? So once again, our g is now just a function of r. That's why this thing. Now differentiating with respect to r, just get partial p gamma upon partial capital R. That's equal to 4 pi g of r squared, right? This is the probability distribution function in r, right? Once again, g of r, since it's only dependent on r itself, you can actually write this thing, or you should probably go for g sub r of r, right? That's a better thing to do. So g sub r of r, you can actually replace that by f sub r of r. Just difference in notation is all. So basically, it's just the probability distribution in r, right? Yeah, in small r, basically. Okay. Yeah, right. So what's I going to say? Yeah, you can actually change this thing. You can change it like f sub r of r, right? Yeah, but this g thing is was actually for the complete volumetric distribution, right? Yeah, so it's different than just the radial distribution. It's really different. So although we have g sub r of r over here, that's not actually the probability distribution in r. Instead, it's just something that you use to like separate this. Okay, that's all it is, really. Cool. So actually, the radial probability distribution is 4 pi r squared times our g of r thing. So g of r is just the volumetric probability distribution in this case, right? Just in this case, because g sub theta and g sub phi are not to be 1, or we set them to be equal to 1, right? Then you can just replace your g, or let's just say you can replace your g sub r by g. Does that make sense? Right. So just replacing that, and once again, like g can be replaced by f sub v, because yeah. So if you say like f sub v at small r, that's like meaning that f sub v at some point where your x squared plus y squared plus z squared is equal to r squared, right? So using that, you can just write this thing, f sub r of r, right? Which is basically what this thing is. So just partial p gamma upon partial r, which is just f sub r of r. That's equal to 4 pi r squared times g of r, right? Yeah. But now recall that, like g r theta phi, that's just f sub v. So actually this becomes like f sub r of r is equal to f sub v at r. So at some point which has x plus y squared plus z squared equal to r squared, right? It should really just be f sub v of x, y, z, but whatever. So it's equal to f sub v of small r times 4 pi r squared. Once again, because this f is actually just dependent on r itself. It's not dependent on theta and phi. So, if the only parameter that you're usually dealing with is small r, why not think of it as a function of r itself, right? Yeah. So then it's just f sub v at r times 4 pi r squared. Now you can multiply divided by dr, and then something very obvious turns out that what it's really saying is that f sub r of r times dr, that's equal to f sub v times r times, well, this thing is like dv but written in terms of r. Does that make sense? 4 pi r squared dr, that's just the volume of a thin a thin shell at a radius r, at a distance r from the center, right, from the origin, of course, ends of thickness dr. So f sub v times this thing is just the probability that the event is going to happen in that volume, right? And then f sub r of r times dr, that's also the probability that the event is going to happen in that volume, because it's, yeah, it's all the points which have our distance from the origin in the range r to r plus dr, right? And that's exactly the definition of f sub r. That's the way it's defined. The probability that this event happens in that range upon dr, right? So this should be actually very obvious, and we didn't actually have to do it in that much of rigor, but still, what we finally get is that f sub r of r is equal to 4 pi r squared times f sub v. But then f sub v can be written like this thing: f sub x of x, f sub y of y, f sub z of z. And yeah, that's it. It's all about the same. On to the next section. So previously we have derived that only in the x direction your probability distribution with respect to the velocity is given by this thing, partial n sub x of vx upon partial vx upon n naught, where nx is the number of particles with velocity less than vx in the x direction only, right? N naught is the total number of particles. So this thing we call it f sub x of vx. This thing is given by this expression square root of m upon 2 pi kt e power negative m vx square upon 2 kt, where vx is the x component of velocity, m, small m, is just the mass of each particle, k is the Boltzmann constant, and T is the temperature of our system. All right. Consider the 3D space given by Vx, Vy, Vz. The volumetric probability density function for this space is given by f sub x times Vx, f sub y times Dy, and f sub z times, oh sorry, f sub x of Vx, f sub y of Vy, f sub z of Vz. All these probability distribution functions multiplied together, that's the volumetric probability distribution function. All right, which is just this thing. It's m upon 2 pi kt to the power of 3 upon 2 times e power negative m v squared upon 2 kt. Remember that v square is actually the total speed squared, which is just vx squared plus vy squared plus vz squared. All right. Right. And yeah, so once again, Vx, that's actually not the RMS velocity, it's the velocity at which you are figuring out the probability, right? Similarly, V is the speed at which you are figuring out the probability. All right, cool. So the radial probability distribution function, that's given by partial n sub x v upon partial v. So v is, of course, is the square root of vx squared plus vy squared plus vz squared. That thing, so partial n sub v of v upon partial v upon n naught. Once again, this small v is different from capital V, which will be the volume. We are not dealing with volume anywhere, right? Okay. This thing is the radial probability distribution function. So this thing is actually given by 4 pi v squared. So in this case, the radius, quote unquote radius, right? In this space of vx, vy, vz, that's just small v, right? So just 4 pi v squared times this thing, right? Times the volumetric distribution function. That's the actual radial distribution function. So this should be obvious, because 4 pi v squared dv is just the volume of a thin spherical shell. That times of this probability distribution function is the probability of finding the event happening in the thin spherical shell, and this is the probability distribution function in the radius. That times of the radius. So here by radius I just mean the velocity, the speed. Sorry, that is also the probability of the event happening in the range v2 v plus dv, which is once again just the thin spherical shell in this space given by this thing. Okay. Right, so this is actually not that hard to understand. You should really watch the last section. Okay, so see my video on 3D order distribution functions for more details. Once again, just that thing, of course. Thus, we obtain the distribution for speeds. We obtain that f sub v of v, that's given by 4 pi v squared, this thing m upon 2 pi kt to the power of 3 upon 2 times this exponential e power negative m v squared upon 2 kt. All right. So for maximum f sub v of v, we take the derivative of this thing with respect to v and we set it to equal to 0. So just get the vmp, which is the v most probable, that's equal to square root of 2 kt upon m. This is actually very well known. The most probable speed is sort of 2 kt upon m. Sometimes people also write it like ump, whatever. Also the average speed, v average, that can be calculated using this integral. So just integration of vf of v times dv. So the number of particles, right, f sub v of v times dv, and that is the speed that these guys have, right? That's what this thing is, or I should say the number of, instead of number of particles, I should say the probability of probability of finding particles in that range, that times of v, right? Once again, you can write it as number upon total number, right? And then this thing becomes very clear why this is actually the v average. But just calculating this thing, what you get is square root of 8 upon pi kt upon m. Cool. Now E equal to half mv squared, that means E equal to mv dv, right? Or dE equal to dv square root of 2 me, which means that partial ne upon partial E is equal to partial nv upon partial E. Once again, you know what this subscript means. It just means number of particles which are having energy less than this thing, right? Less than E. And similarly for this thing as well, right? Which can be written like this thing. It can be 1 upon square root of 2 me, which is just partial v upon partial E. That times of partial nv upon partial v. We already know what this thing is, right? Exactly. So what this actually means is like f sub e of E, that's equal to 1 upon square root of 2 me f sub v. But then, yeah, I mean, this thing is just f sub v. Well, that, yeah, just that thing. But then it doesn't have the n naught value over this. Like, just put that n naught outside and you get this thing. Similarly for here, just put that n naught outside and you get like f sub e of E, right? So those n naughts get cancelled. You just get this equation, f sub e of E is equal to 1 upon square root of 2 me times f sub v of V. In this case, V is just square root of 2e upon m, right? Thus, just putting this value into our expression for f sub v, you will get this thing. You'll get f sub e of E is equal to 2 square root of E upon pi times 1 upon kt power 3 upon 2 times e power negative E upon kt. For maximum f sub e of E, you should have the derivative of this thing being equal to 0 with respect to E, of course. So the most probable E is actually given by whenever V is equal to square root of kt upon m, and not when V is equal to square root of 2 kt upon m. The most probable energies, of course, is kt upon 2, right? So yeah, there's like a difference in that. Okay. Now let's go to the Graham's law, which is proved using this distribution. All right. Consider a particle with x component velocity vx. It collides with a ball 1 at a time period 2lx upon vx, and thus frequency vx upon 2lx. Thus the total frequency of hits received by the ball is this thing, right? Which after a lot of math, you just get this thing. Okay, here A is equal to Lx Ly, V equal to Lx Ly Lz. We know that PV is equal to nRT. Oh, it's nkt in this case because capital N, of course. Then your dH upon dt is equal to this, right? And that's basically our Graham's law done using kinetic theory. Right. Majorly, it's just basically this thing that it's inversely proportional to 1 upon square root of m when you keep all the other things constant, right? So basically just negative dn upon dt, that's the flux through our small hole. That's given by P times the area of the hole, so pressure times area upon all of this stuff, square root of 2 pi mkt. Not very important for our discussion, right? And here's a nice summary of all of this. I'll post a PDF. You can get that summary in that, right? Revise it every day. I don't know what you want to do with it. Anyway, so this section is done. And I guess we should stop here. So I'll see you guys in the next video. Bye.